Hi, everybody. Thank you for joining us today for the fourth webinar in our Essentials series. Today's webinar topic is an educational session discussing adhesive types and how to select the best tape for an application. If you have questions, we do have a chat box available. Go ahead and submit your questions anytime during the webinar, and we'll cover them at the end of the session. To introduce ourselves, my name is Janet Page. I'm the Senior Marketing Manager for the Medical and Industrial Tape Division. I've been with Mactac for just a little over 19 years, the last almost 7 of which have been in a marketing role supporting our industrial and medical tape business. Joining me today is Steve Schroff, and I'll let him go ahead and introduce himself.
So I'm Steve. I'm going to cover the bulk of the presentation today. I'm a business development chemist with Mactac. I've been here about 18 years, 21 years almost in the industry altogether, and the bulk of that time has been spent in various R&D and engineering functions.
Great. So just a little bit about Mactac and our parent company, Lintec. Mactac is based in Stowe, Ohio. We were founded in 1959. In 2016, we were acquired by Lintec. Lintec is a $2 billion company based out of Tokyo, Japan. And our Stowe location, which has been our headquarters since our start, is now the North American headquarters for Lintec USA. Lintec USA comprises a few different companies owned by the Lintec Corporation, including Matico, who specializes in high-end window films, and VDI, specializing in metallized films. In terms of Mactac's product portfolio, we specialize and have since our start specialized in pressure-sensitive laminates for a wide range of markets and applications. First of which is our graphics division. Graphics focuses on materials used in signage, wayfinding, fleet marking, window, wall, and floor graphic applications, and materials designed for wide format inkjet printing. The Industrial and Medical Tape Division, which is the division Steve and I both represent, we specialize in double-coated films and foams, transfer adhesives, and custom engineered solutions for industrial applications. We also have a line of medical tapes approved for direct skin contact, used in wound care, electrodes, and wearable devices. We have a sheets division, and they specialize in label materials used in digital and offset printing. We've got narrow format division focused on narrow format materials used in aqueous inkjet, UV inkjet toner, and indigo printing. And finally, we have our roll label division, which is Mactac's largest business unit, specializing in pressure sensitive label materials for packaging and shipping to UL recognized durable labels and security labeling materials. So now I will go ahead and turn the presentation over to Steve, and he will start today's discussion.
Okay, so today's presentation is going to cover mostly rubbers and acrylics, but we're going to start off just looking at, the pressure sensitives that are out there, the different adhesive chemistries, and there's really 3 of them. You have acrylic, which can be provided in either a solvent, UV, which is 100% solids, that's how Mactac does it, or there are emulsions acrylics out there as well. With the acrylics I will be covering today, I'll be focusing on the solvent and UV. That is predominantly what's used in tapes. You see the emulsion, you're starting to see more in tape applications, but really that's more towards the roll label, the labeling side of it, not necessarily the high performance side of it. Rubber, they can either be hot melt or solvent, and then of course silicone. Silicone is very small of the total market size. Again, acrylic and rubber are the bulk. They make up about 90% of the market. Silicone's really great adhesives. They actually combine all the best attributes of acrylic and rubbers together. They have low surface energy, high temperature resistance, high UV resistance, great chemical resistance. So you might ask, well, why don't we ever see more silicone, or why don't we cover them a lot? And that's because they come at a great price. Really, silicone tapes can cost $20 to $50 an MSI, and I'm being kind of generous there. I've seen some silicones in medical go for as much as $100 an MSI. An MSI is a unit to measure 1,000 square inches. That's typically what the tape industry uses. To give you an idea, if you're not familiar with MSI, we got rubber tapes. They would go for about 75 cents to $1.80 per MSI, and acrylic tapes, maybe $1.80 on the low side to $5 on the high side. So again, when you compare the cost of acrylic and rubber versus silicone, that's why acrylic and rubber really make up 90% of the market. You're not using a silicone adhesive unless you really need it. So today I'm going to cover focus exclusively on the differences and why you should select a solvent, or I'm sorry, an acrylic versus a rubber adhesive. This always comes up. Always seems to be the pressing question, and really, get right into it. The ultimate answer to the question, the answer to the ultimate question of all adhesion is, which is better, acrylic or rubber? Which one makes the better adhesive? And in my nearly 21 years of doing this, I've been collecting a lot of data, and I put it into an algorithm I wrote. And after 21 years, the answer I got back was 42. Put a lot of thought into this, and seriously, hey guys, the answer is 42. Hopefully some of you out there are fans of the Hitchhiker's Guide to the Galaxy. If you're not, then I apologize for the last two slides, but I'm just having a little bit of fun with you. So this is something from the Hitchhiker's Guide to the Galaxy. Don't know if you ever saw the movie or read the book. So, but getting serious now, which adhesive do I choose? And unfortunately, the answer really is it depends on the application, and that's really not much more satisfying of an answer. They both really do have their strengths and weaknesses. Because of the nature of pressure-sensitive adhesives being both viscoelastic materials, both solid and liquid at the same time, it's actually kind of hard. There's really no one-size-fits-all solution, especially, comparing the rubbers to acrylics. But even if you compare different acrylics amongst themselves or different rubber-based adhesives to themselves, it's a lot easier to select and hone in on structural adhesives than it is pressure-sensitive adhesives. But fear not, I'm going to do the best I can to kind of help you guide you through these this disorienting task of what adhesives should you select. And one of the places I always start with is I always ask two questions. And if you were on with me for the low surface energy, the surface energy webinar 2 webinars ago, I posed these two questions then, and that is, one, will the adhesive physically stick to the materials that are being used in the application? And two, will the adhesive survive the application environment in which it's being exposed to? Those are two great questions to start with. Now, today I'm going to be covering all these different components of adhesion, but really those two questions, there's 7 bullet points on here, 7 different things we're going to take a look at. Those two questions I started with cover 5. Will it stick, and is it going to survive the environment? So what I plan on covering today is adhesion both to LSE, and I broke adhesion into 2 parts, and you'll see why. We're going to cover LSEs first, and then we're going to do a little exercise, learn about adhesives. Then we're going to cover adhesion part 2, which would be the higher surface energy type materials and some quick tack. And then we're going to look at holding power, chemical resistance, application temperature, UV resistance, and cost. And, going to go through each one of these, and I'm going to explain, not only what adhesive works better in a lot of these applications, but go through the why they work better in an attempt to educate you so that, you come across an application or you need to try and figure out what the best solution would be. You can kind of go through what I teach you here and be able to formulate an answer yourself. So when we look at low surface energy adhesion, again, if you're on the adhesion webinar where I covered low surface energy, this is a repeat of that. So we're just going to do some basics here of that. Got a chemical up here. Oops, sorry. And now I'm going to put in some dividing lines here. Hesitating on me, and I'm going to show acrylic adhesive here and put in some inflection lines. And really what you see here is that, when you look at the rubber adhesive, there's, if you fold it over on yourself, especially since it can rotate, you don't see a lot of difference amongst the backbone in the rubber-based adhesive. On the acrylic adhesive, however, you do see a lot of difference there. There's a lot of different things going on with the acrylic adhesive. So now I'm putting, you see some little blue areas come on here, and the blue represents areas where there's not a lot of polarity. If you remember the surface energy adhesion webinar I did, we talked a lot about polarity. So in the acrylic, you see these areas of non-polarity. Now the orange here, these are areas where you have a lot of polarity. And the reason why is that when you have polymers, you get what's known as a covalent bond. And what a covalent bond is that, basically the individual atoms share electrons with each other. When you have just carbons and hydrogens, the bonds is pretty equal. Carbon's good people, it shares it pretty evenly. When you start throwing oxygens, nitrogens, things like that into the mix, it starts to become very skewed, and you get areas of polarity where the electrons shift from one side to the other, and you get these polar sites. And you see a lot of them in acrylics. In the rubber-based adhesive, it should all be blue now. And what you see is that there's not any polarity whatsoever. Everything's pretty well balanced out. And so how we can summarize this is that polar materials are high surface energy. They are pretty much synonymous with one another. If you're talking about a polar material, you're talking about something with high surface energy. Conversely, non-polar materials are low surface energy. These are a lot of your plastics and things like that. The surface energy of the material, so this is the rule I talked about before. The surface energy of the material you're bonding to should be higher than or equal to the surface energy of the adhesive itself. This is kind of a universal law in all of bonding, so not only for pressure sensitive adhesives, but for structural adhesives, for sealants, for caulks. Applies for ink adhesion in the printing industry and architectural coating and paints in the building and construction industry. The general rule is you want what you're sticking to be higher in surface energy than the adhesive that you're using to adhere. And so here I have a little animation showing that. So we just got our little drop of adhesive down, it's on the surface, it's forming its bead. So again, for good wetting to occur, the substrate, which is represented in yellow, that should be of higher surface energy than the adhesive, which is represented in red. And you should be able to see some arrows here being animated. And why that should be, why you want your surface that you're sticking to be higher than the adhesive is that the adhesive, you want the surface to be pulling the adhesive out and helping the adhesive wet the surface. Again, when you're talking about adhesives, it's all about wetting. You need to be able to wet the surface in order to make a bond. And adhesives, they have their own internal, we call it surface tension because they're typically a liquid, but the surface tension is pulling the adhesive together and it's working against the force of the substrate pulling the adhesive apart. And so if you have a high surface energy material, that bead of liquid's going to be really low. And conversely, if you have a low surface energy, that bead's going to be high. One way you could think about this is water on a freshly waxed car. And so, just recapping here, materials like polyethylene, polypropylene, TPOs, thermoplast olefins, EPDM rubbers, butyl rubbers, nitrile neoprenes, all of them are going to look closer and resemble more of rubber-based adhesives. I wasn't going to write all their structures out, but just take my word for it. If I did draw all their structures, they would look more like a rubber-based adhesive than an acrylic. If you remember, or if you weren't part of it, I put this in the adhesion webinar we did a couple months back, just looking at the surface energy of common materials. So again, this is representative. The bead is going to be a drop of water and it's going to be in the surface. So here we have low surface energy materials. Water is a very high surface tension material. Liquid, and so the water is going to beat up really high, and you see common things here: polyethylene, polypropylene, EPDM, materials like that. So sorry, next we have the medium surface energy materials. These fall in the middle of the spectrum, but these are really what we call the high surface energy plastics. This is your polyester, Kapton, nylon, ABS, urethanes, and then we have our very high surface energy materials, which aren't hard to stick to at all: aluminum, stainless steel, glass, and porcelain. So up top, I kind of show the range of the surface energy of the adhesives themselves. Rubber-based adhesives are typically about 28 dynes, so they're going to stick to the widest range of materials, and they're going to stick to a lot of the low surface energy materials. Again, you want the adhesive to be less than or equal to the material it's trying to stick to. So if you look in the column, the first column here, polyethylene 29, polypropylene 31, TPO 30. The rubber-based adhesive is going to stick to a lot of those. I do have a red line here of right at the bottom of EPDM, because then you see silicone and TPE or PTFE, which is Teflon. This is the reason why silicone is used as the release liner. Silicone is so far down on the spectrum, the only thing that's going to stick to silicone is silicone. So if you see a lot of silicone rubbers in the industry, unfortunately, a lot of times nothing's going to stick to them other than those very expensive adhesives I referred to in the beginning, which are the silicone-based adhesives. If you look in the middle, acrylic adhesive 38 dynes. Acrylics have no problem sticking to polyester, urethane, ABS, polycarbonate, no problem. And again, the high surface energy, everything sticks to aluminum or stainless steel or glass. So, this is really a good visual aid, and we have this available on the website. We gave this out before of, just a quick reference guide of really showing what adhesives stick well to these materials. And as you can see, just because rubber-based adhesives are so non-polar and so LSE themselves, they stick to a lot of these materials. Now, all is not lost. If you have acrylic adhesives, or if you need an acrylic adhesives can be modified with tackifiers to help the LSE adhesion. These are known as typically modified acrylics, is what you'll hear them referred to in the industry. And what that really means is that they have tackifier added to them. You can add maybe up to 20% tackifier in an acrylic, and this is to help with the LSE adhesion, just low surface energies. Contrary, rubbers always have tackifiers in them. Rubbers have to be formulated with tackifiers. Acrylics do not. Rubbers are usually tackified up to 45 to 55%, depending on the formula. So, the reason why tackifiers help the acrylics is that, one bullet point too fast here. Rubbers also have plasticizers in them. Plasticizers are mainly your oil, and they can vary from, 5 to 15%. So, in some cases, you can add plasticizers to acrylics. That's not very common. They don't typically work very well. Typically, you're only adding tackifiers to acrylics. The reason why that helps is that tackifiers and plasticizers are both LSE materials by nature themselves. So you're putting a low surface energy material into an acrylic, you're helping bringing down the overall surface energy amongst a few other things. So you can make acrylics more LSE, but they'll never be as good as a rubber-based adhesion, or a rubber base in terms of LSE adhesion. So when it comes to sticking to lower surface energy, some of the cheaper plastics out there, your ethylenes, your propylenes, the advantage definitely goes to rubber. So covered the first part, but before we get to the rest of these, we're going to cover a little bit about differences in pressure sensitive adhesive structure. And when we cover that, then all these other things are going to kind of fall in line, and you'll be able to really get an idea visually and mentally of why this is. So quick review here, PSAs are viscoelastic materials. That means that they have both liquid components and solid components, or liquid properties and solid properties at the same time. The best example of this is silly putty. It's a solid, but if you roll it up into a ball and set it on a table and come back 15 minutes later, it'd be flat. That's because although it's a solid, it's also liquid. In order for us, Mactac or any tape manufacturer, we need to be able to physically coat an adhesive, which means we need the adhesive to be more visco than elastic. If you take a look at the tape, all of the adhesive that's on there is several orders of magnitude too high in viscosity to ever be coated out. So we really need to essentially water it down and make it very, very visco versus elastic. And it's pretty simple to do. There's two ways to do it. We can dissolve it in solvent. If we use organic solvents, it's known as a solvent-based adhesive. If we do it in water, it's known as an emulsion. Or we can heat it up to the molten state, and it's known as a hot melt. And again, the whole point there is to really reduce the viscosity of the adhesive so we can coat it. However, after the coating, we need to bring those two properties back into balance here. And really that's done. And this is where we start getting into the real meat of what is different between acrylics and rubbers structurally, and ultimately what drives their difference in properties. Although they're both viscoelastic, they achieve that balance much different, and it leads to these different properties. We can either do this, bring the elastic properties back in balance by cross-linking, or what's known as curing, or we can do it when the adhesive cools. Kind of a spoiler alert here, the cure part is for acrylics and the cooling part is mainly for hot melt rubbers. You look at acrylic adhesive, so if you took that acrylic polymer I showed earlier and you start making big long chains out of it, And then what we can do here is we can add something in there known as a cross-linker. These are compounds that, and what they do is they start tying all of these chains together. So really what cross-linking is, or when we refer to curing, again, cure and cross-link get used interchangeably. What we're talking about is a reaction that occurs between the polymer chains in the adhesive. Now with solvent-based adhesives, solvent self-cross-linking, acrylics mainly, this happens when the solvent evaporates, or sometimes they're thermally initiated. So you get the temperature up to say 280 degrees F, and this will kick off. The other way this happens is UV light, and this is mainly for your 100% solids adhesives. This is the method that Mactac uses, is that we coat these out in a molten state, sort of like a hot melt, but we do it at a much lower temperature, and then we use UV light and we cure them. And what this really does is increases the elastic nature of the adhesive, or essentially the strength. So again, the nice thing here is that if you took a polymer that's already been cross-linked, you're never going to be able to melt it again, and you're never going to be able to dissolve it again. So by not doing that and putting in a solvent beforehand, you've really reduced the viscosity, you coat it out, and then you cure it. And that's how you can have the lower viscosity for coating, but then have the higher viscosity to make a PSA. Again, the other example I use in this is taking maple syrup. Maple syrup is very viscous, it's very liquidy, and it's very sticky. However, it has no elastic strength to it. So whereas, if you get it on your fingers will stick together, but they can very easily be separated. That's because there's no elastic component. And final point here, higher cross-link density really increases the cohesive strength. So on the right side, I have on the top here what a lower cross-link density is. It just means there's less interaction between the polymer chains versus a higher cross-link density, which is, there's a lot of interactions between the chains. Now, one full point here of disclosure, rarely in real life does, you can't expect all the polymer chains to be perfectly parallel to each other. That doesn't happen. It's going to be, a tangled up mess. Think your Christmas lights at Christmas. Everything's going to go in either direction. And in reality, not every single polymer chain is reacted to every other one. When we talk cross-linkers, we're only talking 0.5% to 5%. So what we're really doing is we're building, several, we're slowly creating essentially what you might call gels within the adhesive. Slowly, we're taking individual polymer chains, making them into bigger groups, and those groups get bigger, but they don't all interact with each other. Now we're gonna have a little fun here, and we're gonna look at cross-linking versus molecular weight. So I got some pasta here. On the left, we got some macaroni and cheese with elbow macaronis. And really, if you think of the size of the actual noodle that's being used, you can think of that as molecular weight. Or molecular weight really refers to the size of the polymer. In this case, it's going to refer to the length of the noodle. When you have elbow macaroni, they're pretty small. It's very easy to reach in there with your fingers or a fork and pick out a single macaroni from the bowl without having much problem. It's very easy to pick them apart. On the right, though, you have spaghetti. And that you could think of as a much longer polymer chain, hence a much bigger molecular weight. And it's much more difficult to reach in there and pick out an individual spaghetti without having some entanglement. You can do it, but it's a little harder. And so what cross-linking is that you take the spaghetti and now imagining yourself being able to tie little knots around the individual noodles. That's what cross-linking would be. You have these long polymer chains, and then you further tie them together. That's what these little red things are representing. Unfortunately, I've never seen anybody successfully tie knots around pasta. If you do, or if you're capable of doing that, send me a picture. I like it in my presentations. But what we're really doing here is, by cross-linking, is we're extending the chain length. We're building molecular weight. Molecular weight dominates all your, temperature resistance, your high shear. But again, you got to be able to coat it, and then you want to build the molecular weight. So the cross-linking is building molecular weight by combining the different chains together. If you have 4 chains and you're able to combine them all together, now you just increased your molecular weight by whatever those 4 chains were. Now, rubber adhesives, on the other hand, are much different. So what we commonly refer to rubber today are synthetics rubbers, and they're based on styrene block copolymer technology. And what that is I have a picture here of what a typical rubber looks like. And, you know, we're called styrene and they're called block copolymers because they all use styrene and they're all divided into, they're all segmented into these very defined, distinct blocks. So we have what's known as end blocks, and that's where the styrenes sit. And styrenes are very hard, they're very big, they're very bulky, and that's where all your strength comes from an adhesive. And then in the middle, you have the rubber, and that's known as the mid block. And this is where your different rubber types can be. So it could be isoprene, it could be butadiene, it could be butylene, it could be isobutylene. It could be any type of rubber, but they're always anchored on either side by the end block, which is known, or which is styrene. So, and how this technology really works is it's really a two-phase morphology, and the whole basis of the technology is that the styrene and the mid-block rubber, they are completely incompatible with each other. They will separate immediately, and you know, as soon as you coat them, they start to separate. They are oil and water, they are cats and dogs, they are Democrats and Republicans. They just do not like each other and they separate from each other. And so we can actually show that here. Again, pardon the crude drawing, but what you get is the domain formation. So all your green polystyrenes, they are going to be, so you heat them up, you get them molten, you put them on the web, and as soon as the web starts cooling, again, they're very incompatible, so they start to group together. And in the world of chemistry and physics, like attracts like. So, you know, non-polar is going to go with non-polar, and more polar is going to go with more polar. So all the styrenes form together and they form these end block domains. And again, they're very big, they're bulky, and they kind of get interlocked together. And that's where your strength comes from. And then all your rubber, your isoprenes, your butylenes, they're going to form these really soft middle domains, and they're going to be just free to flow and move about. That's what I have circled here, represented in purple. So now they get their strength, again, just from coalescing together and the entanglement. There is no chemical cross-linking involved. Therefore, hot melt rubbers are what we know as thermoplastic, which means, you know, you heat them up, you coat them, and then they solidify, they form this polymer or this adhesive, but you can heat them back up again. And you can really continuously heat them up and cool them down as many times as you want. If they were thermoset, that means something actually happens. There's a physical reaction that's happening that keeps them from ever coming apart again. UV acrylics that are 100% solids are thermoset. Again, you heat them up, you coat them, but then you're cross-linking them and you're curing them, and then they never break apart again because they're physically linked together. The key here is that rubber adhesives are never physically cross-linked, so they can come apart again. And I kind of show that here. So, you know, here on the left is what it looks like after coating, and then on the right, with the addition of either heat or solvent, you break the individual polymers again. So you have the individual chain with your end blocks, your rubbery middle, and then if it cools down or you dry off the solvent, again, hot melt rubbers can be coated out of solvent as well. They go back into the domain formation on the left-hand side, and that's really how rubber-based adhesives work. And I kind of covered this in all my talking, but the rubbery mid blocks, and I'll cover this a little bit more coming up, they flow around, and so the end blocks, the styrene is what gives it the elastic properties, the structure, the strength, and the rubber mid blocks is what gives it the viscous properties, which is the flow. That's the part of the adhesive that is forming the bond with whatever surface you're sticking it to. So in keeping with the food visuals here, here's my favorite dish. Every time I go home, Mom still makes this for me. It's the only way she can get me to eat my sketties. But if you look at the hot dogs, they kind of represent the styrene domains, and then the pasta noodles represent the rubbery mid blocks. Keeping with the spaghetti noodle pasta theme. So now we're going to get back on track and cover the rest of these attributes. So we're going to look at adhesion part 2. So we covered LSE adhesion, and rubbers have the advantage there. Really, when it comes to any type of adhesion, peel, tack, and shear, but we'll get to shear. But with peel and tack, rubbers still have the advantage. On high surface energy, we're talking stainless steel here. Acrylics max out 10 pounds tops, and a comparable rubber adhesive at the same coat weight, I should say comparable coat weight, 15 to 17 pounds. You just get a lot more peel out of rubbers. Peels have a lot more quick tack values too. You know, typically quick tacks are also 15, 17 pounds as well. Very high. Rubbers reach ultimate adhesion much quicker than acrylics do. So a lot of times you might be familiar with acrylics and you got to let them set overnight, 72 hours, sometimes even up to 1 week. Rubbers, a lot of times they achieve their final bond in 30 minutes or maybe 24 hours max, but they achieve their ultimate adhesion much quicker. You might be wondering, why is this? Well, is it the surface energy? Because, you know, they're lower surface energy, maybe they have other surfaces to wet them out better, but really, you know, everything I just explained on that previous slide in terms of value, this is all for stainless steel. And stainless steel is a whole order of magnitude higher in surface energy than both the adhesives. So it's not really that rubbers are always going to be wet out across the surface better. Stainless steel, aluminum, glass, they're all capable of wetting it, you know, making an adhesive wet out. Even the plastics, urethane, ABS, PET, that's capable too. So if you thought this, it's a good guess, but it's not quite why, and this is why I covered the structure of the adhesives first. So if you go back and look at the adhesive, acrylic adhesive that I showed that's cross-linked, what you really notice is that it's really starting to look kind of like a net. So I have a net here. And so if you want to pull on the net, there's some slack in it. If you want to pull it up towards these handrails, you can pull that end rope, but you're going to pull the entire net with you because everything's interconnected. Likewise, if you want to pull it, you know, off to the side, you can pull it there. There's some slack, but again, everything's coming with because everything's interconnected. Now, on the right-hand side, these kids jump roping, I'm going to use this as a visual aid for describing rubber-based adhesives. The two girls are your styrene domain end blocks. They're firmly anchored there, and the ropes are your your rubbery mid blocks. It could be isoprene, it could be butadiene, whatever. But as you notice, they have a lot more freedom to move around. And then this magically floating kid will give him a role. He's the plasticizer or tackifier. So whenever you add plasticizers and tackifiers to a rubber-based adhesive, they're working on the mid blocks. That's where you want them. That's the mid blocks that's making the adhesion. That's what you want. And really the key takeaway here is that the acrylics, because of cross-linking, they're kind of constrained, whereas the kids with the jump roping here with representing rubber-based adhesives, the chains aren't nearly as constrained. They're free to make a lot better, a lot more movement. So we say that the polymer chains used in rubber adhesives have a much higher degree of freedom, and thus they can flow better. In acrylic adhesives, again, they're more hindered by the cross-linking. And in acrylic adhesives, it's very well known that the more you cross-link them, the more you hurt the peel. So this is really the reason why you get a lot more flow, or I'm sorry, a lot more adhesion out of rubber-based adhesives is that the polymer chains can simply flow out and make much better bonds. The other things too is that rubbers and tackifiers are loaded with plasticizers, and really what they do is they act as lubricants. They have other functions, and that's like a 500 level class, so I won't cover that here, but you can really view tackifiers and plasticizers in both adhesive chemistries. They really act like lubricants. So you have a whole lot of them in rubber-based adhesives. You have these long chains. They're not hindered and tied to each other. Yeah, you get some entanglement, but they're not, you know, tied like that net was. And with all that plasticizer and tackifier in there that's lubricating them, they're just really free to flow around. And this is why they have outstanding quick tack, is they can just physically react to a surface much faster than acrylic adhesive can, because they have so much more degrees of freedom. They can just flow a lot easier. And ultimate peel. So now we're going to cover holding power. And in this presentation, we're going to do a presentation referring to the differences between holding power and shear strength. But for the point of this presentation, you know, you can kind of refer to them as the same. So when I say holding power, I'm really referring to shear strength, or the strength of the adhesive itself. Rubber adhesives have much better shear strength overall as well. At Mactac, our Trip 5 or MP555 adhesives, we need to use a 25-pound weight to measure the shear. The common weight used in the industry is a 1 kilogram, that's 2.2 pounds. If you have a very high cohesive strength adhesive, you know, you might go up high as a 5-pound weight. With Trip 5, we had to use a 25-pound weight because we hung a 10-pound weight 12 years ago and it's still hanging. So obviously rubbers are really, really high shear. They provide really high shear. Rubber adhesives also have much better balancing properties. So not only do they have higher holding power, MP 593, our 593 adhesive or XT, it will hold a 5-pound weight forever. It will not fail, but it still gives you 15 pounds of peel and 15 pounds of quick tack. So, and again, the reason for this is again, as I was mentioning, cross-linking is there to build molecular weight, and molecular weight is what really drives all these properties. The problem is that, you can get an acrylic to be as firm as a rubber-based adhesive, but the problem is that the acrylic ceases to be a pressure-sensitive adhesive then. Again, with acrylics, the downside is that as you increase the cross-linking, they become too hard, they become too sterically hindered, and they don't flow anymore. And so you lose a lot of your peel and a lot of your quick tack trying to increase your shear strength. And ultimately, because they'll never be as long a molecular weight as a rubber, they'll never have as high a shear. And that's everything I kind of covered there. So I'm going to go back to this diagram with the spaghetti. So do nothing to the left, the bowl of spaghetti. So your spaghetti pasta is usually about a foot long in length. You break the pasta in half, put it in the bowl. So, foot to 6 inches in length. To be more accurate, the image on the right, which is the spaghetti stuck in the hot dog, in reality, the hot dog pieces would have to be rings of kielbasa, maybe 12 or 15 of them strung together on either end, and the actual spaghetti noodles would have to be 5 and 10 foot in length. So that gives you an idea of how much difference in molecular weight there is. Yeah, the rubbers aren't cross-linked, but they are very long molecular weight, and those end blocks really get entangled, and so you just get a lot more strength out of them, and that's why you get the better holding power. However, now we're coming in areas where the cards start to flip. So when you look at application temperature, first we're going to look at low application temperature, and it's pretty even Steven with these two. Both acrylic and rubber are pretty even for low temperatures. They both have about the same application temperature for general purpose adhesives and the service temperature. Some confusion here. Application temperature is the temperature at which you apply the adhesive, and service temperature is the lowest rating that adhesive is good for. Again, an acrylic general purpose, a rubber-based general purpose, you're going to apply them both about 45 degrees Fahrenheit, and they're going to be good to about as low as -40 Fahrenheit. Both adhesives can be formulated to be freezer grade and freezer applied, or low temperature adhesives. And again, both of them can be formulated so that they can be applied, physically stuck to the surface at -20 degrees F. And that would drop the service temperature to as low as 60 degrees F. Now, the one thing I will say is Lintec, our parent company, they do have cryogenic adhesives. And so they're one of the only ones that do have cryogenic. And when you get into a true cryogenic adhesive, which is considered -80 C, the acrylics are going to have the advantage there, mainly because the lowest rubber is 60 degrees C, and some acrylic monomers are lower than that. But in tape performance, we typically don't see that low. So in typical tape performance, it's going to be on the low end, pretty even between rubber and acrylic. However, when you get to the high temperature, acrylics are far superior for adhesive for higher temp application. It's hands down acrylic on this one. Even the worst acrylics can outperform the best rubbers. The problem is again, the end blocks is where you get all the strength, and they're capable of providing a lot of strength for a rubber-based adhesive, but they can only do it at room temperature or slightly elevated because they're not physically bound together. So again, they're thermoplastic. They can go and remelt again. So what happens with rubber-based adhesives is that you reach the melting point or the softening point of styrene, which is around 95 C, just shy of 200, maybe around 185 F. And they start to melt, and everything starts to become a liquid again. It becomes more viscous and elastic, and you start losing your bond and losing your strength. Again, these are thermoplastic, which means they can melt again, not thermal set. And so I go back to this drawing again, and in this case, I circled the heat. Your adhesives on the left, where you have your nice domains, everything's honky-dory. You add some heat in there, and you get what's on the right, which is everything breaks down again. So with acrylic adhesives, acrylics can withstand 450, 500F. Now, again, that does depend on formulation and that does depend on application needs. When I say application needs is if you just need an adhesive to stick to a surface, yeah, you can get up 450, 500. If you need the adhesive to hold a lot of weight, well, that top end temperature is going to drop drastically. Again, top end temperature isn't a finite, it's really up to interpretation and it really isn't based off of what you need. And some of this does depend on formulation. Just because something is an acrylic doesn't mean it's going to get you that high. Only certain acrylic adhesives are going to get you that high, certain crosslink levels. And ultimately, if you need something as high as 450 to 500, you're going to be trading off some peel and tack. Like conversely, though, rubbers, the very, very best rubbers will max out about 220F. And again, you could get 220F out of a rubber, but only if you really just need it to maintain a bond. Because again, as these rubbers melt, they still are sticky. But if you need something to really hold a weight or something, the top end of rubbers is going to fall drastically. Most rubbers fall into the 160 to 180F. Our Trip 5, something that's very unique, will get you up to 220. But again, if you need that to hold a lot of weight, it's going to vary a lot. And that temperature is going to come down very far, very drastically, I should say. Going to cover chemical resistance. Again, because acrylics are capable of physically cross-linking between the polymer chains, it makes them much more chemical resistance than rubbers. Acrylics rely on a chemical bond. Chemical bonds are not easily broken, and rubbers rely on mechanical interlock, and that is something that can be very easily reversed. So, and again, here, if you look at solvent or chemicals, it could be a solvent, it could be a plasticizer, it could be motor oil. Again, you're going to break up those domains and really cause the adhesive to come apart again. So again, acrylic resistance is very dependent on formulation and crosslink density. That's when I say, it's not a one size fits all solution for this. Different acrylics do different better with different chemicals, and others, again, some acrylics have a higher crosslink density. Now, the one thing here is that acrylics won't dissolve, but they can swell. So some acrylics compared to rubbers are considered hydrophilic, and rubbers are very hydrophobic, means water loving, water hating. And although acrylics can be cross-linked, if they are hydrophilic in nature, although they won't dissolve, they will swell. This is the concept of hydrogels. So if you have a hydrogel, those little bath beads, the things that you put in plants and add water to and they hold the water, those are hydrogels. And they're not dissolved, but they do expand. And then when they expand, they lose their toughness, they lose their rigidity. So you have to watch it. If you're going to be using an acrylic in a aqueous environment, you might not want a hydrophilic acrylic. You might want something that's more on the hydrophobic end of acrylic, even though they're both cross-linked. That could go for plasticizers. Certain acrylic adhesives are very good for use on the graphic arts type of materials because they are more plasticizer resistant versus some other acrylics, which, yeah, even though they're acrylic and even though they're cross-linked, the phthalates of the vinyl will still destroy them. When you look at rubbers aren't very chemical resistant, but because they are very hydrophobic in nature, you can use rubber in contact with very polar compounds such as water, any type of detergent water, or alcohols. There's such a difference in polarity. Alcohol, even though it's a solvent, will not be able to dissolve a water or rubber. It won't even be able to touch it. This is the reason why motor oil a lot of times doesn't come out in the laundry is that because rubbers are so high molecular weight, even if you have a detergent in there, it can't properly dissolve them. So if you're using rubbers, say bonding sponges, I've seen an application where bonding sponges together and they were used for cleaning. Again, water and detergent will not, affect a rubber adhesive at all. In fact, a lot of times a rubber will withstand that environment far better than an acrylic because an acrylic can swell. Another thing is swimming pool patches and things like that. A lot of times those adhesives are rubber. Again, rubber might not have chemical resistance when it comes to organic solvents or oils or things like that, but in water, rubbers are actually, can be better. Where they do fail, though, is rubbers often soften in the presence of organic fluids. So we're talking gasoline, we're talking diesel, oils, hydraulic fluids. I covered plasticizers and vinyls, and certain foams have them, or organic solvents, toluene, heptane, hexane, etc. So if you start talking, I want to use a tape under the hood of a car, around in the bilge of a boat where, gasoline or diesel might be, in certain gaskets where, the gasket's going to be there sealing around oil. Those would all be very bad areas for a rubber-based adhesive. Again, they're not physically cross-linked. The oil is just going to go in there. It's going to act like a solvent. It's going to break up those end block domains, and everything's going to fall apart. So coming up on the end here, so UV resistance, acrylics do have better UV resistance as well. Both acrylic and rubber adhesives will yellow with UV exposure. So it's a bit of a misconception that acrylics do not yellow. Acrylics do yellow. They just don't yellow nearly as much as rubbers do. Now, I'd say both chemistries can be partially or fully hydrogenated to reduce the amount of yellowing. And what that means is it's a lot like the, here, hydrogenated oil. So I'm going to show the rubber-based adhesive here. And you see a lot of double bonds, and everywhere there's a double bond, sorry, I gotta go through this. Everywhere there's a double bond there, that is what tends to break apart and react with oxygen and yellow. You do see some double bonds in the acrylic there with the oxygen, but that's a much harder bond to break apart with UV light than with just ambient UV light from the sun or from the lighting inside an office than the rubber-based adhesive. But that is the area, and that's why they tend to yellow. Now, what hydrogenation does is that it breaks that bond and it puts a hydrogen on there instead of an oxygen. And so you're left what's known as water white, which is clear and not something that's going to yellow. So I'm just going to get through the slide. Now, another advantage, though, is that although acrylics will yellow, not as much, but they do yellow. Even if they do yellow, they tend to remain stable. And what I mean by remain stable is that they're not going to break down as much. Rubber-based adhesives, they will yellow and they will break down. So over time, if you put a rubber-based adhesive in direct sunlight, you get maybe 6 months out of it. It depends how much antioxidants in there, but even if you load it up, you're not going to get much stability out of it. So one misconception then is that rubber adhesives cannot be used for outdoor applications. They call it weatherability, and that is true and false, but again, it depends on the application. A rubber-based adhesive can be used outdoors if it is not exposed to direct sunlight. So if there's something there that's not, blocking it from direct sunlight, rubber-based is fine for outdoor. So an example I use here is that you don't want to use a rubber-based adhesive around windows. Windows are translucent. They're going to allow the UV exposure to get in. That's going to hurt the adhesive. But rubber-based adhesives are used all day long for roofing underlayments. Again, it's outdoor, but it doesn't have any direct exposure. So that's kind of one of the things you got to think about, just because it's going to be outdoor exposure and exposed to the elements, rubbers are perfectly suited to work in aqueous environments. It's just if it's shielded from the sun, you're good to go. If there's going to be sun exposure, it could be a problem. Last slide here is cost. Pretty straightforward. Rubbers are more economical than acrylics. Most of the components that are used in rubber-based adhesives are byproducts of other industry. The rubber themselves usually come from the refining of petroleum into gasoline, diesel, kerosene, jet fuel. And then, synthetic rubbers really came about. It came about in World War II, one, because the U-boat fear of sinking the ships coming back from South America with the natural rubber, and also because we had all this excess raw material left when we cracked and distilled oil. What do we do with all the leftovers? Well, somebody figured out that we could make a synthetic rubber out of it, and that's where block copolymers came to be. And they were first used in synthetic tires for World War II. but because they are a leftover byproduct, most of the time they are very cheap. Your tackifiers as well, you know, when you harvest trees for the paper industry, if you ever see some videos on YouTube, then they go back after they cut down the trees, there's a machine that goes back and rips out the stump. This is where all your rosin's coming from, your rosin esters and things like that. Fruit peels are used, you know, in the orange juice industry, they take the peel, they make terpene tackifiers out of that. So because they're leftover components of a lot of different industries, it makes them very cost effective. And inversely, then acrylics are very refined polymers. There's a lot of processing that gets done to turn petroleum oil into acrylic acid, to turn it into butyl acrylate and things like that. And because acrylics are highly refined, they are more expensive. So that is the end of that. This time we'll open up to any questions that there might be.
Great, thank you. So Steve, one of the first questions we received is, what type of adhesive is best for mounting on top of UV coated substrates?
So typically UV coated substrates, it depends what the coating is. I've seen UV coating substrates be both epoxy based, which is very high surface energy, and some of them are a lot of silicone. So you see a lot of UV cured coatings in the packaging industry, and the silicone's there for low coefficient of friction. So it really depends. Rubber will stick to them both, and if it's epoxy based, acrylic will stick to that as well. That's a hard one to answer. It really depends what that coating is. I will say a lot of times people see that it's a UV cured coating, and the UV does not play into that at all. Doesn't matter it's UV cured or if it was thermally cured. It just depends what the base chemistry is and what the surface energy of that chemistry is.
Okay, great. And so if the attendee who submitted that question has a follow-up, you can go ahead and submit it by chat. In the meantime, we do have another question, and it's do rubber adhesives meet guidelines for indirect food contact?
Yes, and they can even meet guidelines for direct food contact. Rubbers are very inert, again, because we're talking synthetic rubbers. They are very inert. The rubbers that are not inert and cause irritations and things like that are the natural rubbers, and that's because of the natural protein that comes from the tree. A lot of times, like our medical rubbers, when I formulated them, I was using the same grade of rubber that was used in food components. So it might shock you, but like if you're chewing gum right now, chances are you're actually chewing on a synthetic rubber. And so rubbers are good for indirect and direct food contact. You just have to make sure they were tested for those certifications.
Great. Do any of the other components of tape constructions impact performance? So things like carriers, for example?
Oh, they certainly can. So I was focusing on the adhesive. And most of the applications out there, the carrier will be considered inert essentially. But if you want to have a 450 to 500 degree adhesive, you can't have a PET. You got to either have a foil or I forget the trade name. I think it's Kapton, the polyimide, polyimide type films. So when you get into those type of applications, you're going to need something of higher temperature on the film itself. So it's irrelevant if the adhesive can withstand that temperature, if the carrier cannot. Conversely, foam. So, this is where some of the high-end acrylic foams really come into play. Is that a lot of times people use those high-end acrylic foams, and I won't name trade, and there's a lot of generics out there for something where they don't need it. A polyethylene foam would do just fine. However, when you get into high temperatures, though, again, if you have a polyethylene foam, even if it has an acrylic adhesive on it, that polyethylene foam is, if it has an acrylic adhesive, the polyethylene foam is going to melt far before the adhesive is going to let go, most likely. In terms of LSE or ultimate adhesion, not really. Phase doesn't matter there. UV, obviously there are different grades of films out there can withstand UV, but if the film, technically, if the film degrades, it doesn't necessarily mean the adhesive is going to degrade. The product's probably still going to fail because the film failed, but the adhesive might be just fine.
I believe that is it for all of our questions today. So thank you all so much for attending.